Hello Internet! This time audio is on. Welcome to Fun Project Monday, a live stream where we design something nice, no deadlines, no managers, and have fun. While enjoying a beverage, I have coffee. I like this. So, yes, let's... we are still working on our LED controller, and now I tried to restream. Now we are on different platforms. Let's see how this works. So, I have taken a look on what I did 2 days ago. Let me open that. And this. I don't want that. So that's good. Yes, we are working on the front panel. We searched for a few buttons we can use. We searched for a rotary encoder we can use on ARCSC. And that worked out pretty fine. Even the bottom... Why is that so bright? That doesn't look good. Why is the background so white on this tree? Why? Okay. R28. So. Now it looks normal again. And we did some concept how we want to build it up, and how to make our buttons and our indicator lights. Of course, at this part here, with a sinus of 30 degrees is 1/2, so our button indicator light will be the same. Diameter as the difference between the bottom part of a front plate and the front plate PCB. Another thing is that I wanted to talk about is that the distance here. The distance here are roughly 8 millimeters, and it's important that we have, that value, because you will need to add an spacer which has that particular distance. And I took a look on my drawings this morning, and oh wait, I want to have another screen here. Take the distance, and so okay, I wanted to have another distance here, and that should be 8 millimeters or something. It's important to know it because we will need to order spacers which fit those. And yes, that is great. That's really great. So we have a concept for our front plates. We could go right into designing it, but we won't do it right away. We will do some. We will take a look on the power stage. We'll take a look on what parts to use, on what parts we don't want to use, and things that come around on that front. So let's talk about the power stage. And I want to change that so I can see everything better. Great. So the most easiest, maybe not the best way to implement it, would be using one of these. So to rehearse what we want to do, we want to have following setup. You want to have a supply voltage, double P, and from that supply voltage we need to get some sort of DC-DC converter. From that we will power our LEDs, so here come the LEDs. And back this DC converter, a control logic. Let's draw it in. How we call it, switches. So some sort of control logic, and of course we need that 3 times. And if we take a look on, and we had some requirements for the power stage. Requirement 1 was, yeah, maybe use the right letters. It needs to supply 12 volts and 5 volt. Both from the same controller. Of course we could use 2, that would be great for efficiency, but a total cost disaster. Of course you could say, we don't want this, we don't care about costs, but I don't care about cost. At least a little bit. And of course you need to assemble it and everything. We use one. I use one controller. So it needs to be switchable. Needs to supply 3 amps. Well, were there other requirements? No, not really. And if we say, okay, we want the most basic approach on solving this would be using these ready-made DC-DC converters, which have an LM2526, 2527, something like that. I think the 27 is a step up version, but they have some sort of DC-DC converter with big power brick, and you can solder the potentiometer. You can solder it out at your own resistors to change the this DC converter to the value you need. I done that in one project once. But of course it's a lot of... It is relatively... oh, I see. There's something I should change. There are 2 things I should change. Let me do a quick black screen. Yep. That was too much. We'll be back in a minute. And we're back. And of course that's great, but the efficiency from the LM2526 is, from what I've researched, not that good. Of course, first of all you have a big power brick. That's not really that's not really a good indicator for an efficient device. Mostly I think it's bipolar. And of course you need to solder those, and the quality of the PCBs is of course not so great. Of course you can solder them, and actually it's not such a big problem, but I don't want to do this. It's not efficient enough. So we're going to use some sort of other DC-DC converter and add our own circuitry. Another thing that we will discuss is how to add all the different... what will we discuss? That's a good question. Is how we do the switching, and what we should not do, what kind of not optimal solutions we will use, because having a 12 and 5 volt supply is of course a challenge with one controller. because either you have a controller which has two outputs, so you have two inductors and two everything, or let's not stay on that page, let's change the page. Let's go to browser, yeah, change here. And let's think, let's take a look on the part that I have decided to use. It's let's go to LCSC. It was the TPS 54302. Even name-brain part, no Chinese knockoff or something. Let's take the first best guess. Fortunately, relatively expensive. I need to check what the difference between two bows is. That one is more cheaper. Let's take that. Chinese datasheet, that's of course not optimal. Maybe the other one is not in Chinese. Okay. Let's get one like that. TPS. TI. We don't want that. And let's get a data sheet. Here. So, okay. Of course, this part is relatively efficient. Unfortunately, they don't give us the data up to 3 amperes. That's the area that I'm more interested in. But, yeah. Maybe that's it. Has a built-in MOSFET, so we have relatively low, so we don't burn our power away with bipolar one. That's great. And here we have the typical layout of such a DC-DC converter. The problem is, I think they had a table down at the bottom, is that depending on the kind of voltage you want to output, there are of course values for the inductor, for the capacitors, and for the resistors, which are optimal. Here it is, and using or enforcing two outputs from the same controller is not ideal. I am interested, like this project is, I'm interested how it will behave if you don't put in the right values. But because the efficiency at 12 volts, because 12 volts 3 ampere, that's 36 watts, that's a lot of power. We will do the following. We will build up we will use that part, and we will add the recommended values for the 12 volts voltage. And use it in a not optimal mode for the 5 volt supply. We can measure afterwards how it behaves. Do we get way much more EMI? Can we make a difference? We can even populate a PCB with. We can even compare the EMI differences between those two. Maybe we do that. Maybe we don't. Yeah. So we will work with that. Of course, there's a lot of calculations you can do for the different capacitor values. I didn't take a look on that particular, although I have lots of experience with designing DC-DC converters, so I'll read that one other time in peace. But we will first of all say We will stick with those values. That would be pretty good. It will. So, after we have discussed that, we can start putting the schematic together. Because now we talked about 3 hours, I think, about what we want to do and how we want to do it. So I think it would be a great idea to start doing at least something. Okay. Yes. Let's change the... yeah, we will start with schematics. I will change to another screen. So, for schematics, I will use DipTrace because DipTrace is a design suite which is great. It is so easy to use. A few days ago, I had to use KiCad for another project. It was required to use KiCad, and it was not a pleasant experience to work with KiCad again. Unfortunately, it's a great project. It's impressive what they have put together. It's really impressive, but I think it's still very it's not as user friendly, especially for new users to work with. So I'm happy I bought DipTrace. It's great. I will use that. So let's start very simple by putting some nets down. We want to have, was it here? Brings wire display spin Unfortunately, it's some time ago that I used it the last time, so I will need to net ports. But I want to have that, and we will start adding our supply voltage. Let's start with an plus 24 volts, our worst case input supply. We will add a ground. No, VSS. And we'll start using the using one of the more recommended or rebuilding. Let's change. And we'll start by building in one of those example circuits, because why shouldn't you? They've done all the work for you. It will most probably work correctly if you do it like they supply it to you. So you're going to use this. So let's start. Let's see if the TPS is even part of that. Search areas, libraries, TPS 5.4. Let's see if we get one, or if we need to put it in ourselves. That's another thing DipTrace is really good about. The if you want to create new components, it's so easy. It's I like that system. With other EDA packages, it was always kind of, let's say, it was always a little bit not easy to do it, but with DipTrace it's great. So let's add a new component, because it's not in the libraries. And we will do user components. I didn't import my all my libraries in Dypress yet, so we will not use it. So we'll do everything new. I most probably port it sooner or later. I want to have an okay. My VM just broke. Oh, and I didn't change the screen, so you didn't saw anything. Great. We're back again. Let's see what our virtual machine says. Oh, it still runs. The manager, a virtual machine manager did fail, but the machine itself did run smoothly without problems. That's great. So we can continue. So of course it's a view TI. Let's put in the datasheet. Why not? Ah, okay. We'll put it in later if we do it. Then we choose a pattern. If we take a look on the data sheet, it's then SOT23. Let's take a look. We have it already in our SOT23 with a pitch of, what's the pitch? 0.95. Okay, I think the streaming software just broke. Let's see if we get back on. Are we back on? Okay, Odyssey we're in. Okay, we're back. So, fortunately the right pitch is already available. Okay, they want us first to do this. Can we use the pattern generator? Can we use it? Template. No template. We need to do it by ourselves. I think it's obvious that I didn't touch the software for some time, but that's not a problem. We will add 3 pins. 1, 2, 3. That and like that. 3-pin. We have a 3-pin packet. So now we're already online. Okay. So we have a 3-pin package. You need text. Let's take a look on what we will need to add. Let's take a look. Where's the pin out? I think it was up here. we'll have I'll put v in the top. V in. The great thing about we don't have to copy the layout of the pin one by one, or by the IC one by one. We can change it so we can put it nicely in our datasheet, and I will do this. So we'll put the V in enable and ground complete on the left side, and we add another text. We'll put in boot switch and feedback. Okay. We have manufacturer TI, ref design is U. Okay. Then ground V in is pin and V in is pin 3. That is enable is pin. That's pin 5, that's correct. Ground is pin 1. The bootstrap pin is pin 6. The switch pin is pin 2. Okay. And the feedback pin. Oh, come on. Is pin number 4. So now add a pattern. Want a 95 pitch. Oh, that's not correct. SOT 23.6 pitch with 95. So, and now we have from every possible manufacturer a variation of a pitch. I will choose that one that is seems to be the most compatible with the pitch that is supplied or recommended by TI. So I have 2.7 millimeters or 200. Maybe one of these 270s, and can we find another difference? 4 times 0.5. Let's check if that works. Let's check if it works to add up the 0.6 times 6, and we come to 7.4. No, that doesn't help us. That does not help us at all. Also, or any other 75, 174, 145. Yeah, now we have still a few. But now the difference is not that big, and for first go I will simply take this one. Should be good enough beginning. Okay, save. Good. And now we should be able to use it in our, yep. Good. Now let's change back to the let's change back to the reference circuits. And now we will simply build it by ourselves in libtrace. Where is it? Here it is. We won't populate the what we want to is populate the values. The values themselves, we will check them later to fit our application. So we'll add with capacitors. Before I use some, because in libtrace you have a lot of different let's say it. Okay, wait a minute, this JSC, that's new. I didn't know that library yet. So you get, okay, that's nice. So it seems like you get all the basic stocked part at JSC PCB. That's actually very fortunate. But we won't use it yet. We simply work with simples. And after that, first of all, work with the simples. And later we can change it. So we'll start by placing a few resistors. Placing a few caps. And far. Cap non-polarized. Between the feedback divider, I have definitely a non-polarized cap. And that most probably circuitry gets another non-polarized and a few polarized. Add those here. And we'll put in an inductor. From iron core. Okay. We will assign later the corresponding values, because if you assign them later, it's way easier. I want to have straight lines. So that will be our enable pin, and our enable pin Okay, now it gets interesting. Okay, I need to stop fucking studio modus. Okay, with that, enable pin, they have a divider here, so I'm interested if we are not allowed to put the full voltage on. Let's search. Enable. Float the pin to. Float the pin to enable, okay. Enable threshold. On off her device when the voltage exceeds the threshold for operation. Support below. Okay. The enable pin has an okay, so the floating is the floating seems to be optional. Question is, are we allowed to put on? Okay, we will still use the divider. So we'll add a MOSFET. So of course we want to have the option to enable and disable the power supply. And we can do this by only switching on or off the different LEDs, but I think it would be a good idea to have a possibility of adding an a extra or adding a complete off power voltage, and we will do this. Or simply add a low side MOSFET in. You want to have an and he will add an via add to net. Want to create a new net. Enable channel 1. Okay. So because that will be a relatively big schematic, you don't want to have wires going everywhere where it is not adding to the understanding of the schematic. So we will very simply add a net that we will connect later and a ground. So, does that make sense? We assume that we put that on the enable pin. That doesn't make sense. So, this circuit itself should create a voltage. If you take a look on the reference circuits, which is just above the 1.28 threshold voltage. Go back to the converter here. So that will definitely create a voltage to keep the pin alive. So we may add, we will cut this via to okay. So we put it in series with nothing. We put both to ground. So as soon as we turn on the MOSFET, the voltage at this point will go to 0. And we're happy. That's great. So let's continue. That is both ground. Let's put it a little bit to the side. Like that. Looks nice. And connect this. Yeah. Connect the V in. And of course you want to change the screen. So if we turn on that MOSFET, the voltage at this point will be 0, so the device will be turned off. That's what we want. And that should be everything for this part of this circuit. Let's make this a little bit nicer. Let's check that. So now we have the boot circuits. And now we can implement the rest of the circuits. Bootstrap. That. We add all of this to the side. Make it smaller. This switch. Can we make that? No, that does look shit. That looks good. Add these two caps. They have most probably used two caps to bring the series resistance down. So add those, add those, the last resistor. And we will add ground. So the ground. Add that one. So that capacitor is most, I think, used to dampen the system a little bit. And that should be enough. I think we have a via symbol in here too. Or let's condense that a little bit. That's okay. Put that together. Put this together like this. Yeah, we'll condense everything a little bit so we can copy it later and doesn't need to be that big. Can be smaller. Should also be. It doesn't look good. Put this on one. So that's okay. See, does it look bad? Oh, that's okay. Here we will add another via. Simply call that net6 channel 1 out. And I want to have a connection at that point. So let's give it an arrow. Oh, that doesn't work. Don't want to have this. Should have one out. Okay. We will add this later. Where was the possibility to add some name to it. And we'll add this ground here. So let me check something. Okay, that works, and I don't have a time. Yes, I have a time now. Great. Oh, we are now online. That's great. So that will be around about the circuit we will use, and now I can start adding some values. That will be. We'll add them later because we will most probably try to optimize them later too. And now's the point where so many things come together that it gets somehow complicated. Yes, no, we don't want this. We don't want this. So let's add let's add some recommended values. Like I said, if you take a look in the data sheet, for 5 volts there's 10 microhenry coil recommended, and for 12 volts 50 microhenry. We will stay with 15, so we get the most possible performance. Do we get a mu? We get a mu. Great. So 50 mu. C2. C2 is not really not that important. These are both properties. 22 microfarads, correct. And that is a ground. That is a ground. Come. Okay. Good. Then we will add we can start populating C1 and C2. Where's reference? Reference is here, okay. 10 microfarads and 0.1. Because most of them are not that important, and we most probably will change them later again. 0.70 to consolidate the cost of the bomb. We'll do this. A feedback. Yeah, here we will certainly need to change something, because we want to have changeable output voltage. So here we will add another resistor in parallel. And that parallel resistor, okay, now I have, great. And that parallel resistor will get a MOSFET, because we want to change the output voltage. And for that, that is change voltage channel 1. Ah, that was wrong. No. Value is changed. Yeah, that's great. That's great value for MOSFET. Net name, and we will disconnect this first. Delete from net. And add to net and channel. Change voltage channel 1. And we'll also add a small capacitor at this point to add some dampening to the voltage change, so we don't get some unwanted response. Oh, that has the right value, great. I'm happy with this. Okay. That looks good. Oh yeah, we can certainly make that a little bit more compact. But for first, that's good. Yep. And that will be around about our power circuit. Now, of course, we could start adding the although, let's think about it. Some description. So, yeah. So, channel 1. Power circuit channel 1. Okay. So we built this 3 times. And now I'm thinking on what I always forget to change the screen. I will need to have another solution for that. Certainly need to have another solution for that. Okay. Now we have done this. Let's find out what the difference between these two parts are here. Because we have an price difference of nearly 100%, and I want to know what's the difference between DCCR and DCCT is. Yep. Let's take a look if we can find some we can find some information on that. Okay, there's certainly at TI the price difference is not that high. Okay, let's check the data sheet. Not that one. Some one that I can read. CCT. Packetron, DCC, DCC. Ah, okay, the package quantity is so different. Do I want to believe that? Because they are both... Seems like we are both the same. Aren't they? Yeah, it seems like the only difference is the package density of the... Oh, do they have two different reels they sell? No, they don't. Okay, so then it's the same part actually, so it doesn't matter. I will certainly bookmark the cheaper one. Yes. Let's start another discussion. Connectors. So we have done this. First of all, we'll save the save that. So we didn't done another really important discussion yet. We need to think about the kind of connectors we want to use for our device. And I think there are around 4 different options which are applicable. that will be mini XLR, mini DIN, and we would have maybe another connector which I couldn't find or really couldn't source here in Germany or on eBay and everything. It's the 3.5mm Klinke, or it's that headphone jack that nobody wants to build into their phones anymore. Because I think the different connectors have an... So okay, let's roll back a little bit. One important thing for our connectors is that they need to support 4 signals. Actually, they need to support 4 signals and 1 signal with really much power. So we need 4 to 5 pins. And I didn't believe it, but there exists a 4-pin they are headphone jacks which have 4 pins, and that would have been one option to use. But problem is they need to be able to handle the current. That's a thing I don't know. At least 3 amps on ground pin, or 3 amps on the big one, and relatively 1 amps on the smaller ones. So I'm interested if they are available. Of course, that's more or less an maybe not the ideal solution, but this pin or this connector, it's relatively small. It is unfortunately not easy to source. I thought it was, but only the 3-pin connectors are easy to source. And it's it was 4-pin, yes. Or did I thought about a 5-pin connector at that time? Did I? I'm not prepared with this. I'm doing this impromptu, this connector discussion. No, these 4 pins should be relatively easy to source. I think there was a 5-pin headphone jack that I thought about. No, there isn't. But that brings us to our next option. So these 4-pin headphone jacks are actually a viable option. Of course, there are DIN connectors. Of course, DIN for Deutsches Institut für Norm. They are relatively cheap and available because it's an open standard. Everybody can build them. And another option would be Mini XLR, because they are also relatively small. You get them with a locking mechanism on the 4-pin. Do we have 4-pin in? Yeah, we do. Yep, we do. They are relatively easy sourceable. Every kind of connector jack combination. And like I said, they are small. And if we think about our model, we need to appreciate the fact that we don't have so much space. If we have our enclosure, the bottom is full of PCB which emits some heat. The top is relatively big because we have around about 1 centimeter intrusion into the whole case. We don't have so much space, so we need to and we don't want to use a way too big enclosure that is not very elegant too. We need to find a solution which is not that big, and that could also be an option, but we can try to find if we can source something which is which fits our need. Let's take first look if we can let's find out if we can work with those categories. Circular connectors, that could be something. Wire to board, pin headers, nope, 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 nope. Audio connectors, rarely available. And that's everything we can use. We are able to use, and let's look. If we can search for mini XLR from the beginning. Okay, we only get XLR as a search term. We get different headphone jacks. Oh. Or that all headphone jacks, that would be... I think that are all headphone jacks. Let's take a look on the more expensive ones. I have the assumption that JSC PCB is putting some very cheap parts in the first page to get you hooked on the parts, and then you can find from the really cheap ones a more expensive sub part that you can really use. Yeah, but it are all... What? Yep, that are all headphone jacks in any possible variation, so we don't want to use those. Let's check for mini XLR. First of all, like that. No chance. I want to change that again. Okay. So, we want mini XLR, we want to have some connectors. Card edge connectors. I don't think that search will be very fruitful. And I suppose that we mostly get XLR parts. Okay, we have Neutrik in stock. That's of course interesting. They're relatively expensive, unfortunately. They have a very nice panel mount system. Okay, let's check for female sockets. 3 ampere current rating. Let's see what kind of parts those are. I think they're personally are very cheap. They can, yeah, but they are 3-pin, no. Let's try searching from connectors on the ground up. No, we had circular connectors here. You want 4 pins with a high current rating. It's here. Let's see what kind of parts JSC can supply us with. 4 amperes, of course, good too. I have only 1 part remaining, yeah, no. That's not an option, 5 ampere, 17 parts remaining, but if we have 5 ampere sockets, they would be relatively big, don't they? They seem to be, or obviously standard aviation connectors. It would be a possibility too. Fortunately, we are not describing the kind of... Oh yeah, that are definitely the standard aviation connectors. They are an option, of course, too. And these are too fancy. Let's take a look. Let's take a look on these ones, because that is only the. Because if you buy those, you would need to buy the surrounding part too, and then it gets more expensive again. I get the impression that what kind of standard is that, or is that some self-spin? Okay. They don't give any hint on what they are, fortunately. Or let's compare them with an aviation connectors for an aviation connector. Are that those? I don't want to buy something. Doesn't look like that. Yeah, but most probably use those. I can source them relatively easy here, or from another manufacturer. They should be available without no problems. Of course, those sensor connectors, the M-type connectors, they're an option too. They can be relatively cheaply sourced. But I think if I remember correctly, the current capability is not that great, and if it these beefy pins is of course way better. And they are more available, I suppose. Okay, let's check if they are somehow searchable. Because now that's everything that JLC provides. Do they have anything here? And it doesn't look like. No. No, it doesn't look like anything we could use, unfortunately. So we most probably don't source connectors from JLC. Maybe we can. Yeah, that are not really applicable search terms and filter options. We'll take a look on this later. Or we can simply look at eBay. To get here's an. Could take a look on AliExpress, but regarding customs and everything, I think it would be cheaper to source them directly from eBay or some other. Yeah. Look, aviation connectors you wanted to have. The GX12, maybe we can find those search terms. We saw those, then we saw those on Ali, on the JSC, no, we didn't. Yeah, you can get one for, oh, that's directly out of China. That's a direct import, that's direct import 2, direct import 2. That's everything direct import. Everything direct import. That's of course not very good. No. Let's see if we can get something directly out of Germany. can get these. Okay, €1 per connector, but I think that would be the bottom of the line one, so €3 per connector, yeah. Not really an option, because €0 is too much. We need to get those cheapest, but 12 millimeters, that's not too big. We can certainly build that into our device without any bigger problems. So yeah, we'll need to think about those later. Okay. So now let me check something. Good. Or maybe get nope. Don't want that. Should check something under here. Okay, that should be now clear. So, yeah, I think we stop the stream for today. And on the next streams we'll work further on the schematic, add in more parts, adding a complete circuit for one channel, and put some additions to the power supply. And after we have added the everything else, that we can change the voltage, so we are happy, and change the voltage so we can use the 12 volts and the 5 volts LEDs in one go. We will then copy it and do some more, design the front panel, complete the front panel design, so we can start building up the PCB and going from one step to another, handing us to the finished product. Thank you very much for watching, and see you.